So continuing with our discussion on stability. So there are two methods by which we can understand stability using Lyapunov, the direct method and the indirect method. In the indirect method, we use the linearization process, find out the eigenvalues and determine whether equilibrium point is stable or not. In the direct method, we deal with the notion of energy function. We'll be defining stability now for nonlinear systems, and we'll be basically looking into three different types of stability: the Lyapunov stability, uh, the asymptotic stability, the exponential stability, and also the global asymptotic stability. We'll be looking them through the perspective of a nonlinear system, and we'll be understanding how a nonlinear system can be defined to be stable or not through where we'll be defining these different stability criterions. So the first, the Lyapunov stability criterion, which will be the direct method of explaining how Lyapunov analyzes the system for stability. So the definition goes like this. Uh, so for any equilibrium point, or any equilibrium state, not for any, for an equilibrium state, uh, x equal to 0, which is actually the origin, we can say the equilibrium point will be stable for any, if for any real valued function r greater than 0, there will exist another real valued number greater than 0, such that the norm of x at the initial condition is less than r, then such that if for any initial such that if you have a norm of the initial states of the system are less than r, then the norm at any time t will also be so for any value of time t greater than 0, uh, the norm of the states of the system will be less than r. If this is true, then the system will be stable. Uh, Otherwise, it will be unstable. So this is a definition of the Lyapunov stability. So for any equilibrium state x equal to 0, if we have two real valued numbers, capital R greater than 0 as well as small r greater than 0, then if the norm of the states of the system at the initial condition is less than small r, then the norm of the states of the system for any value of time t should be less than capital R for the system to be stable. If it is not so, then the system is unstable. In simple words, if we have a ball of radius r and another circle of radius capital R, then any function uh, that will lie uh, that any trajectory that will start from, say for example, here this is x0, it lies within this unit, within the small circle r. This is point x0. If a trajectory remains within the confines of this loop, then the system, if this is trajectory number 1, another trajectory will remain within the confines of the capital R, and you have third trajectory that will be moving out of this. So you have three different trajectories. The initial condition lies within the circle of radius small r. Then trajectory 1 refers to an asymptotically stable system. Equation number 2 refers to stable system. Now when we'll be saying this is stable, we mean actually this is Lyapunov stable. And third trajectory actually refers to an unstable system. So you have the initial condition of a system x naught lying within the small circle R, and you see the trajectories of the system. For stability, the states xt should not go out of this specified radius, that is capital R. If it is within small r, then it's not only Lyapunov stable, but it's also asymptotically stable. But if it is within the confines of capital R, then it is Lyapunov stable only. But if it moves outside the radius of this capital R as well, then it is an unstable system. So this is the definition of Lyapunov stability. So Lyapunov stability criterion basically simply states that the equilibrium state is stable, or whether it's Lyapunov stable. We can also decide whether it's asymptotically stable, or if it is as well an unstable system. So next definition refers to the asymptotic stability of a system. So again, an equilibrium point x equal to 0 is asymptotically stable if it is one Lyapunov stable and additionally there exists some real valued number r greater than 0 such that the initial states defined by the norm of the function is less than r. That means for all values of time tending to infinity, xt tends to 0. Right? So as t tends to infinity, if your states of the system they are approaching um, the origin of the system, we can say the system is asymptotically stable. So in a two-dimensional space, the time variation uh, can simply be represented by uh, an exponential curve that's decaying to zero. So again, we already highlighted this here also. So if the system is within the confines of this, if your trajectory of the system is within the confines of small radius r, where r is any real value number greater than 0, then the system will not only be Lyapunov stable, but it will also be asymptotic stability. Fine. As we discussed in continuous time systems, in linear systems rather, we discussed Bibo stability and asymptotic stability. We implied there also that asymptotic stability does not always, Bibo stability does not always imply asymptotic stability. If a system is Bibo stable, it may or may not be asymptotically stable. In a similar way, if a system is Lyapunov stable, it may or may not be asymptotically stable. But on the other hand, asymptotic stability always meant Bibo stability. In a similar way, asymptotic stability will always mean that your system is also Lyapunov stability. Fine. So asymptotic stability means that the equilibrium is stable and your system uh, will converge towards the origin as time t approaches infinity. Fine. If in this case, in terms of asymptotic stability, we if your system is Lyapunov stable, but the second condition is not met, wherein as t tends to infinity, your states of the system do not tend to zero, then in that case the system is said to be marginally stable system. Right? In the domain of asymptotic stability. It is still the Lyapunov stable, but as far as asymptotically stability is concerned, it will not be asymptotically stable. It will not be called asymptotically stable. It will be called asymptotically marginally stable system. Fine. Uh, so this is second definition that was dealing with the asymptotic stability of the system. For a Lyapunov stable system with xt not approaching 0 as t tends to infinity, then the system will be marginally stable. It will not be asymptotically stable, it will be marginally stable when we will be talking in perspective of asymptotic stability, but it is a Lyapunov stable system. So this is second definition of stability for extended nonlinear systems. Third definition of stability is that of exponentially stable system. Definition number 3. So an equilibrium point is we'll be understanding the Lyapunov's direct method as well, but for that we need to understand those different types of definitions of the stability in case of nonlinear systems. So an equilibrium point is said to be exponentially stable Fine. We do not, so in case of nonlinear system, we talk about the stability of the equilibrium point. We do not talk about the stability of the system. Uh, Such that if there exists two positive numbers alpha and lambda such that for all values of time t greater than 0, the norm of this function is less than alpha, and uh, the norm of this function is less than alpha, less than or equal to alpha multiplied with the norm at initial conditions e raised power minus lambda. Fine. So for all values of time t greater than 0, if the states of the system uh, do not actually converge towards this particular function, that's alpha times the norm at initial conditions multiplied by the exponential function e raised power minus lambda t, then the system is said to be exponentially stable. So it will actually imply that the function, the states of the system will be exponentially varying functions governed by those two positive numbers, alpha and lambda. Again, extending a rule here, exponential stability will always imply that the system is asymptotic stable. So this will actually imply that your system is moving towards 0, your states are decaying towards 0 much more quickly, or approaching the initial conditions of the system much more quickly as compared to the asymptotic criterion. So exponential stability always implies asymptotically stable system. But reverse is not true. So your so if your system is asymptotically stable, it may or may not be exponential stable. Fine. So you have actually three things here now. So far, one is your function is Lyapunov stable, that may or may not imply asymptotic stability. Now your function is asymptotic stable, that may or may not imply exponential stability. So in case of asymptotic stability, your function basically converges towards the origin equilibrium point as time t approach infinity. But in case of exponential stability, this decay is much more faster, and even the rate of exponential convergence is actually governed by the lambda here. So if lambda is much larger, this decay will be much more quicker. So the exponential stability helps us actually in determining whether your system is bound with respect to time, and what are these boundaries within which the system is confined with. These are three definitions so far. Now we'll be talking about the fourth definition, that is globally asymptotic stability. So if in simple, if asymptotic stability holds true So if your system is asymptotically stable for any initial states, then in that case, that equilibrium point uh, will be asymptotically stable in uh, in general, and it will also be known as globally asymptotic stability. Fine. Same way goes true for exponential stability. If your system is exponentially stable for any initial values, initial states, then the system will be called globally exponentially stable system. Uh, if it is not true, then there may be local stability. The system may be locally stable but not globally stable. If all the initial conditions of the system are not uh, stable, the equilibrium point will not be referred to as being globally asymptotic stable. Uh, in general, linear time invariant systems may, as we already discussed, may or may not be asymptotically stable, and we have defined the asymptotic stability of linear time invariant systems in terms of the eigenvalues of the system, and as well as talking about the global stability. Mm, Whatever be the initial conditions of the system, the stability is uh, the same, remains the same, it does not change. So, linear time invariant system, if it is asymptotically stable, it will be globally asymptotic stable as well. But same is not true for uh, a non-linear system. So we can take an example here to see. For example, we have x dot equal to minus x square, fine, or you can say dx by dt is equal to minus x square, which implies dx by x square is equal to minus dt, and integrating this. So this x raised power minus 2, x raised power minus 2, integration of this is minus x minus inverse minus t plus the constant of integration, that is c. So in other words, we can also write this as 1 by transferring this side, this becomes x is equal to 1 by t minus c. Rather than writing minus c, I'll write plus c because this is still a constant of integration only. So for an initial condition that's satisfied in this case, for x0 equal to 1, if you substitute t equal to 0, uh, t equal to 0 means 1 is equal to 1 by 0 plus c, that means c is equal to 1. Therefore, the solution of this system is xt is equal to 1 by t plus 1. So as t tends to infinity, xt tends to 0. So you can see that this system, for any initial condition, if you take, say for example, x naught equal to 2, 3, 4, c will be accordingly 1 by t plus c, whether it will be 1, 1 by 2, 1 by 3. So this refers to an exponentially decaying function. So as t will tend to infinity, whatever be the value of c here, irrespective of the value of c, that will actually be determined by the initial condition of the system. As long as it is a positive value, the system will tend to infinity. So So in this case, for x not equal to 1, if this is your equilibrium point of the system, any initial condition, as t will tend to infinity, the system will tend, the xt of the system will tend to 0. So you can say this system is globally asymptotic stable. So today what we have done is we have covered four basic definitions of nonlinear systems that are extended to nonlinear systems and how they are different from that of linear systems. So we are actually dealing with Lyapunov stability. We have defined the indirect method. We have to find out how we can define whether the system is stable using the direct method of Lyapunov stability. Using the energy function, we'll be defining that in the next class. So here you need to understand you have three stability criteria for nonlinear systems: a Lyapunov stability criterion, an asymptotically stable criterion, and an exponentially stable criterion. So if your system is exponentially stable, that means it's also asymptotic stable as well as Lyapunov stable. The reverse is not, however, true. If your system is Lyapunov stable, it may or may not be asymptotic stable. If your system is asymptotically stable, it may or may not be exponentially stable. So we'll take up Lyapunov direct method, how to understand it, how to define it,